So let's talk a little bit more about footprints for our components and how they differ from the symbols that we've been using thus far. So when we've been creating our circuit schematic using these abstract symbols here, we know that these don't actually represent real-world components because an LED in real life doesn't actually look like this little triangular symbol with two arrows coming out of it. Or a resistor is going to look more like an actual little ceramic device with two metal leads coming out of it rather than a little squiggle. Uh, what a footprint is, it's the actual copper or metal layout on our printed circuit board that corresponds to the symbols that we have on our schematic, so that whenever we switch over to our PCB layout editor, KiCad knows to take each one of these abstract symbols and translate that over to an actual real world layout. You'll see exactly what that conversion process looks like, but first we have to go in and manually select a footprint for each one of these components. Let's start with the most difficult one, which is the USB connector right here. The process of adding footprints and other details to our actual components is called annotation. There are a couple of different ways we can do this in KiCad, but I find that the easiest one is just to, as you are building your circuit, double click on each one of your component symbols and then fill out the rows that show up in this symbol properties menu. Let's go over what each one of these fields do. So in the reference field up at the very top, that you can see by default says J1. That is sort of like it's an indicator code to the manufacturer or whoever is assembling this board that this USB connector is placed exactly where you see a J1 on the board. It's basically just translating between a bill of materials, this whole long table of components that you have, to where does each one of those components actually go on the board. So we typically are okay just leaving those reference designators as they are. KiCad automatically increments each time we add a new component. So if I was to add a second USB connector to our schematic, it would be called J2 automatically. So I will leave that as it is. The value field is something that we actually want to customize. For instance, we used a symbol from KiCad's pre-made library called USB_A. What this doesn't tell us is that we want specifically to use a USB-A male connector, because USB connectors come in two different polarities, male and female. And the version on the USB battery bank that we're trying to connect to is female, so we need a male to be able to plug into it. So I'm going to change the value field to indicate this. I'm going to call it USB-A male. If you want to see what that change actually looks like on our schematic, you can go ahead and press OK to apply the changes, and you'll see that this text right above the symbol has changed, right beneath the reference designator. So that makes it really easy to glance at the different components in your circuit and see what each one of them are doing. So now I can go back into that symbol properties menu by, again, double clicking on that component and then edit the remaining fields. Let's skip over to datasheet. Sometimes whenever you're using more niche connectors that aren't as widely available or as universally recognized as just a USB connector, you might want to include the datasheet for a very specific part. This is usually a link to a PDF that the manufacturer provides to show you, for instance, what each pin on the component does. For us, we're using a fairly generic USB connector, so we can get away with just leaving this one blank. I'm going to delete the tilde that was automatically generated for this default component. Now, the last row is description, and for this, you can use this for a lot of different things. Some people like to enter part numbers for very specific connectors, or I tend to include a description of what that component is doing. So in this case, I would type USB-A male connector for power input. It's important to note, however, that whatever you enter in this field is not going to show up on your schematic. This is more just for reference for whenever you're going through your bill of materials later to determine what each connector or what each component was for. So you can be as verbose or concise with that as you like. You could type paragraphs and it wouldn't make any difference. It doesn't actually crowd the schematic anymore at all because it doesn't show up there. You have the option to make it show up by checking the little box in the show column on the right, but more often than not, you can get away with just leaving that as is. Now, you'll notice that I sort of skipped over the footprint field, and that's because this is the most fun, and by fun I mean usually the most time-consuming part, which is selecting the actual real-world representation for what this component is going to look like. Basically, we want to translate from this generic rectangular box into an actual set of copper pads that will be on our printed circuit board for a physical USB connector to solder to and remain in place on our circuit board. I mentioned earlier that we're using a bunch of components for this design that are already included in KiCad's libraries, so we don't have to go out hunting for more niche or nuanced connectors or components. Like I said, will include a video later on in this series that will show you how to find those more niche components and how to import them. But for now, let me show you how to search through KiCad's built-in libraries to find a footprint. So let's click into the footprint row in this table, and you'll see that a little icon appeared over all the way on the right that looks like two little books standing vertically and then a third book sort of lying on its side a little bit. This is to indicate that it's a library button. We can double click on that to open the menu, and you'll see that this window is called the Footprint Chooser. It's very similar to this menu that we use to place a new component, to place the schematic symbol, but now instead of an abstract representation of the component, we're choosing an actual real-world layout for the component's different pins. So in this menu, you can search for USB, and we can scroll down in this list until we find a USB-A male type connector. And sometimes you'll have to click through the different options available, read through their descriptions, maybe even take a look at the linked data sheets to see what the exact pinouts are on each component, to see if they're compatible with your design, so on and so forth. Just at a glance, we don't want to use a USB 3 connector because they include a bunch of extra data pins that we have no use for, since we're only pulling power from USB here. So let's look for a USB-A plug. You'll see that some of them are labeled receptacle. That's the female variant of the connector, whereas the male variant is called a plug. So I think that Molex makes one of those. This one does not say plug, so I'm not confident that will work. What about this one? Here we go. So clicking on this to select it, you'll see in the description that it says USB Type A plug, horizontal. And you'll see what the actual footprint looks like and how this differs from our schematic symbol. While our schematic symbol had just a rectangular box with different little lines to represent each pin, this footprint actually shows us what the different copper pads on our printed circuit board will look like. So it has two different shield pins, both labeled pin number 5. It has a V-bus pin, pin number 1, D-, which is data minus, pin number 2, data plus, which is pin 3, and ground, which is pin 4. At this stage, we want to make sure that these pins in the footprint chooser are the same numbers as the ones that are in our schematic. So I'm going to double click on this to tentatively select it for now. And we can take a look at our schematic symbol right here. And you'll see that it is indeed pin 1 for V bus, pin 2 for D-, pin 3 for D+, pin 4 for ground, and pin 5 for the shield. The reason that this is really critical is because regardless of what connector we use inside of our footprint chooser, KiCad is automatically going to map the pin numbers that are used on the symbol to the same pin numbers that are used on the footprint. You'll see what this looks like whenever we switch over to our layout editor. But for now, this is all we need to do for selecting the actual footprint. We can click OK, and that symbol is now finished annotating. We have to do the same thing for every other one of our components in this schematic. So let's go over to our LED. If you double click on that, it'll open the symbol properties menu. You'll see that it has a reference designator, which by default is D1. You'll have a value field, which is labeled LED. We could change the LED field here, but I'm going to leave it as LED by default because that's already a pretty good description of what this is on our board. We have our datasheet field, which I'm going to make empty. You can leave the tilde there, it doesn't really matter. These are, again, more for your reference than anything else. So if you're not using it to actually store a datasheet link, you can just leave it blank. We have a description, which, again, I like to fill in with an actual description of what that component is doing. So I'm going to call this main flashlight bulb. But again, that is entirely up to you, and we could very well leave this blank and be perfectly fine here. Now you'll notice that this LED has a field that the other component, the connector, didn't, and that's a sim.pins row. This is for a feature in KiCad where you can actually simulate your circuit. You might have heard of a SPICE-based simulator. KiCad has one of those built in, and you can define different parameters for your components here. We're not going to be using the simulator in this project, so we can either leave that as it is, or we can just delete the row, which is what I'm going to do here. I'm going to select that row, and then click on the little trash icon underneath the table, and that'll go away. All of these other fields, even if we're not using them, like the datasheet field, we cannot delete. These 5 are required for every single symbol on our schematic. So now we have to, again, choose an actual footprint for our component, which we can do by clicking into the footprint row and then clicking on that little book library icon. Now let's search for LED, and you'll see that there are many, many options for different types of LEDs here. Let's say we want to use the same standard through-hole LEDs that we saw in Tinkercad. So it looks something like this right here, this little red bulb. Oops. Let's try and find a footprint that has a similar layout to this. This is a 5mm diameter LED with an anode and cathode through-hole terminal. So going back over to our footprint chooser, let's see if we can find one in this menu that looks something like that. This is an opportunity for us to talk about 2 different types of components that can be used on PCBs. You'll see these acronyms a lot. One of them is SMD, and the other one is THT. SMD means surface mount device. That means that the component doesn't actually poke through the board at all. For instance, on this same board I showed before, every single one of those connectors is an SMD connector. Nothing pokes through the board except for this row of pins over on the end. Again, not sure if you can see that with my camera blurring everything out, but all of the bigger connectors that are actually soldered on there are SMD components because they just sit right on top. They don't poke all the way through. That's what every line in this SMD category is going to be. The ones that we saw on the breadboard in Tinkercad are called THT components, or through-hole technology components. For that, we can scroll all the way down to the THT section. Here it is, LED_THT, and then we can pick exactly what type of component we want. I said that the ones that we used in Tinkercad are 5mm LEDs. So you'll see there's an LED underscore D5. There are a few different options here. We're going to take a look at our just the one that says underscore D5.0mm and nothing else after it. And this looks pretty similar to our actual LED device, our LED simulated component inside of Tinkercad, where it has pin 1 is K for cathode, even though cathode is spelled with a C. There's a whole story behind why they didn't actually use a C for that label, but besides the point. The other pin is A for anode, the positive terminal of our LED. This footprint should work it should work perfectly for what we need in this design. So we can go ahead and select that by double clicking on it. But if you are interested, feel free to take a look at some of the other components that are available to us. There are tons of different kinds of LEDs that we could potentially select from. If I was actually designing a flashlight to be extremely bright, I would probably pick a bigger LED or maybe one of the branded surface mount components. Like I know a lot of flashlight LED bulbs are made by this company right here, so I might select one of those. These tend to be extremely bright, but just for the sake of simplicity and sticking to what we saw in Tinkercad, let's just use the LED underscore D 5.0 mm in the THT section. So I'll double click on that, and we now have our footprint selected. So that makes our J1 USB connector annotated and our D1 LED annotated. Now we have to annotate our final component, this resistor right here. Now, inside of an LED circuit like this, we always need to include a resistor in series with the LED to limit the amount of current passing through it, because an LED by default will pull just about as much current as it wants, as much as its internal resistance allows, which in a lot of cases can wind up burning out the LED and or destroying the power source. In this case, we really don't want to fry the USB port on our battery bank or whatever else we're plugging this into. So we have to set a resistance value here to limit the amount of current going through the LED. Now, just off of memory, those LEDs, those 5mm LEDs that we saw in Tinkercad, tend to have a 5-volt voltage drop, or no, sorry, a roughly 3-volt drop across them, and they usually take about 20 milliamps. To make it so that we have a safe current going through it, we can use maybe a 120 ohm resistor, right? Again, just off of memory. There's a whole process for calculating the actual resistance that you'd want for the maximum brightness of your LED, but I'm going to save that for your circuits class so that we don't have to take up any extra time explaining that calculation using Ohm's law here. But take my word for it that a 120 ohm resistor should work just fine here. So we will type inside of the value field, we'll replace the R underscore US with 120 for 120 ohms. And we want to specify the unit for this component, because a lot of times whenever the manufacturer, the person who's actually assembling our boards for us, is going through the part list, they will use the value to choose specifically what resistor or capacitor to stick onto the board. So if I just left this as 120, maybe they would misread the R1 and not realize that this is a resistor. Maybe they would pick a 120 microfarad capacitor instead, right? So to avoid that confusion, we want to specify ohms. A couple ways we can do that. We can type out ohms quite literally like this. We could use the ASCII keyboard key to type the capital Omega symbol for ohms, or what the industry standard is to just use a capital R for resistance. I know that it's not the same as an ohm, or it's not the same notation as an ohm, but it's much easier to type a capital R than it is to type an omega on a keyboard. So basically most schematics that you read will use R for resistance. And if you provide this to just about any PCB manufacturer, they'll know that the R is referring to ohms on a resistor. So we have the correct value here. Again, we don't need a data sheet for this, and I'm going to give it a description stating current limiting resistor for LED. And now we finally just have to give it a footprint. Now, there are many different footprints for LEDs. It's easier to use a surface mount LED, an SMD, surface mount device LED, than it is a through-hole one, just because they're easier to find on the market. Manufacturers have a much easier time ordering them in bulk than ordering a bunch of the through-hole resistors. So I can search for resistor and see what comes up. You'll see that the first category is a resistor underscore SMD for surface mount resistors. If I collapse that menu, you'll see that the one beneath it is through-hole resistors, resistor underscore THT. So if I did want to use one of the bigger resistors, I could pick one of these. And this is a physical representation of what the resistors we saw in Tinkercad would solder through. But typically we want to stick with surface mount resistors for resistances this low, just because they're much easier to obtain, and they're more common, and they're way cheaper than through-hole resistors. So we're going to go back to the SMD section. You'll see that there are a whole bunch of options here, and they all have these number codes. What these codes correspond to are the actual dimensions of the LED, the resistor. The 0201, I think, is 0.02 inches by 0.01 inches, and then you'll also see that it has a second set of values with metric by it, which is 0.06 millimeters by 0.03 millimeters. These are very small components. If my camera wasn't blurring it out, I would show you exactly what they look like on one of these boards I have next to me. But typically, if you're hand soldering something, or there's any possibility that you'll want to hand solder it, you don't want to use anything smaller than an 0603. That's 0.06 inches by 0.03 inches, or 1608 metric. So this is pretty much the standard size that I use for almost all of my designs. If your resistor has to take a much higher current and needs to be tolerant to more heat, you might want to use a bigger one. Something like the 1206 resistors. These are quite a bit larger than the other ones. But for our purposes, our flashlight is taking a very low current, so our 0603 should be perfectly fine. So I'm going to double click on that one, and you'll see that our footprint field is now filled in. And that just about completes the annotation that we'll need to do for our schematic. The next step would be actually creating our PCB layout. But before we do that, there's one more thing that I want to show you inside of the schematic editor that is a very good practice. And that is, if we go to this button up here that says Edit Symbol Fields and click on that, you'll see all of the different, those same fields that we saw whenever we opened up the Symbol Properties menu for each component. You'll see them all listed in a single table for all of the components in your schematic. You can even toggle which columns or which values in that menu are visible here. For instance, I'm not interested in the Do Not Populate, the DNP field here, or Exclude from Board, Exclude from Simulation, so I will uncheck them in this menu on the side so that I don't see them in the Show column. I will uncheck DNP right here, exclude from BOM, exclude from board. So now we're only seeing the fields that we're actually interested in. Oh, I'll actually uncheck datasheet as well, because we're not all that concerned with that. But what I wanted to show you in this menu that is very important if you're planning on having this board manufactured by a different company, by some factory somewhere, is you want to add a field for the part number for each one of your components. For instance, for our LED, well, let's start with our USB connector, because this one is given to us by the footprint. The part number is right here. It's already included inside of the footprint. Now, I'll tell you that it's usually not that easy. The footprints are usually something you have to dig for a little bit, and I'll show you that in a second. But I'm going to go ahead and copy that part number, and then inside of this menu on the left hand that shows all of the different fields in our bill of materials, I'm going to click on the plus button to add a new row. And I'll give this row a name called manufacturer part number, or you could also just abbreviate it to MPN. That's also universally recognized as manufacturer part number. If I click OK, you'll see that if we scroll down to the end of our table, each row now has an MPN column as well. I already copied that part number from the USB-A male connector. I'm going to click into that field, and I'm going to press Ctrl-V to paste it. And now, if I sent this design off to a factory to get it assembled, they'd know exactly what part number to use on this board. Now, you may be wondering, why do I have to specify a part number if I already specified that this is a USB-A male connector? Well, there are tons of different connector manufacturer companies like Molex in this case, or TE Connectivity, or Amphenol, or so on and so forth, and they all make very slightly different USB-A male connectors. So even though they do functionally the same thing, the pins might be spaced out a little bit more, or maybe they have an extra shielding pin or something. Basically, the Molex one that we designed this board for will not be directly substitutable with one that another manufacturer makes. So we have to include a part number indicating exactly which component we are using on this board. Just to show you that this part number is something that will be easily recognizable by another manufacturer, if we go back to our browser and then go to a site that sells components like that connector, let's go to DigiKey. They're the biggest, digikey.com, and then I paste in that part number and search for it. You'll see it takes us immediately to the USB connector that we are trying to use. So that's what our other manufacturers would be doing as well. They would just be plugging in the part numbers into a sourcing site like DigiKey, and then ordering those components and then mounting it on our board for us. So for our USB connector, that was easy enough because the footprint already included that part number. But what about the LED and the resistor? Well, the resistor it's very, very easy to find a 120 ohm resistor with the 0603 footprint. Just to show you what that looks like, if I go back to DigiKey and I go down to passives, resistors, and surface mount, and then I specified that I want a 120 ohm resistor that is the 0603 package, and then I see which ones are in stock. There are 144 different options from various manufacturers. Some of them have, hundreds of thousands in stock. So we could specify, if we want our manufacturer to only assemble using these components from Panasonic, I would copy this part number right here into that MPN field for our resistor, like this. And now, if we send this design file over to our manufacturer, they will only order exactly this component and put it on our boards. Now we have to do the same thing for the LED. And again, 5mm LEDs are super common. So if we want a very specific one from a very specific manufacturer, we have to tell them what the part number is of that LED. So we'll go over to LED indication discrete. I will specify that I want a, let's see, I typically do not order through-hole components. This might take me a second here. For device package, we want a 5mm, and we want through-hole. And I'm also going to filter by in stock. And we'll see that a bunch came up here from, again, various different manufacturers. Let's say that we want to use this one right here. This is a green LED, so we're making a green flashlight. I'm going to copy that part number and then paste it into our MPN field here. And again, this makes it so our manufacturer knows exactly which LED from exactly the manufacturer that we chose for that component whenever they're assembling our boards. And just like that, we can click OK, and we are done annotating our board. And finally, we can move on to actually laying out the board, drawing all the traces, and then getting this ready to be ordered.